Hi, and welcome to Quotient Space. Today we're going to talk about numbers. There are a lot of different kinds of numbers in the world, like integers, fractions, rational numbers, irrational numbers, real, imaginary numbers. And I think that a lot of people don't have a clear idea why we have these different number systems and how they relate to one another. So that's what this video is about. It's less a history of numbers and more an overview of the common number systems that we use and how they build on top of one another. The impetus for this video came from a discussion I had with a friend about the term imaginary numbers. Now, this is a terrible name, which is why mathematicians don't use it. Mathematicians call imaginary numbers complex numbers. And for my friend, complex numbers were introduced so badly in high school that they have a block about understanding them to this day. And I think that's a common experience. Usually it goes something like this. There's a number called I, which is equal to the square root of -1. It's called I because it's imaginary. Excuse me, teacher, asks any reasonable student. Didn't we learn last year that you can't take square roots of negative numbers? Well, yeah, we did learn that, but we were actually kidding about that. You can totally do it, and this is how, and, well, learn how to do arithmetic with this because it's going to be on your test. That's basically how it goes. I don't know about you, but for me, that's not very convincing. And so, in the interest of being better convinced, I have put together a brief history of numbers, and by history, I mean overview. The main points I'd like to cover are as follows. First, our notion of number has been expanding over time, actually over the course of millennia, because, hey, it's useful. We keep encountering new problems or things that we'd like to represent that require new numbers. Complex numbers are no more or less imaginary than any other number system. And like imaginary numbers, a lot of our number systems are kind of badly named. We'll see a number of examples of this. Probably one of the earliest number systems to be used in human prehistory was something like the numbers 1 through 10. But as you can imagine, this won't get us very far. For example, what if I wanted to add 5 and 6 together? And since I can always add one more number, it would behoove us to just continue this number sequence on infinitely. So let's add those in. I'm going to call the resulting number system the natural numbers. That's the numbers from 1 and up. These numbers are very intuitive. They correspond to literal discrete quantities, right? I can have 2 oxen, or 3 beans, or 4, well, those are supposed to be gold coins, but they look more like Cheerios, so 4 Cheerios. But while the natural numbers have the advantage in being intuitive, there's a limit to what they can be used to represent. For example, what if I have none of something? I can't represent that quantity with this number system. I also can't subtract a number from itself, so there are a lot of subtraction expressions I just can't evaluate in this number system, so we better add 0. I'm going to call the new number system the whole numbers. And I should say here that the terms natural number and whole number are not standard in the mathematical literature. Some people will say that 0 is a natural number but isn't a whole number. Some people will define them both to have 0, both not to have 0. For our purposes, we just need to be able to distinguish between the two, so I'm going to say the natural numbers are 1 and up, and the whole numbers contain 0. Now, while it seems obvious to us to include 0 in our number system, this was actually a big advancement in number theory. The idea that 0 is a quantity that you can do arithmetic with, just like other quantities. But there's still a lot of things we can't do. Like, what if I want to represent not just the absence of something, but specifically a lack of something? I think the easiest example that I can think of this is something like debt, right? If you owe someone something, you have less than $0 on hand. Also, in the whole numbers, we can't subtract a larger number from a smaller number. This equation can't be completed. So, to fix these problems, we're going to add in negative numbers. The resulting number system is called the integers, which is represented by a capital Z. Don't ask me why. Now, this number system extends infinitely in 2 directions, positive and negative. This is another big conceptual leap forward. If you want to start naming some numbers imaginary, I think negative numbers are actually good candidates. I can't have -2 Cheerios. That doesn't make sense. What quantities do these represent? They're pretty abstract, really. But, on the upside, they do allow us to solve any addition or subtraction equation, so in a very real way, this is a more robust number system than we had before. But the integers are not the be-all, end-all, and to illustrate why, let's engage in a little thought experiment, shall we? Imagine that you have 1 pizza, and then you eat a slice of pizza. Now how many pizzas do you have? Well, you don't have 1 anymore, but you have more than none. Thinking more abstractly, what if we want to be able to represent ratios or proportional relationships? Or, arithmetically, solve certain division equations like 1 divided by 2. I think it's clear what we need to do. It's time to add fractions. This gives us a new number system called the rational numbers, numbers of the form a over b, where a and b are integers. The rational numbers are another of our kind of badly named number systems. The word rational here is literally just the adjective form of ratio. This has the same Latin root as the common English word rational, but this doesn't mean that rational numbers are somehow more pleasing to the rational mind. The rational numbers are represented with a capital Q for quotient, so we should really call them the quotient numbers. That would be less confusing, but we're stuck with rational. Up until now, it's been obvious every time we added numbers to our system that we kept all the ones that were there before. But the rational numbers look pretty different as a set than the integers, so we should take a moment to note that all integers are rational numbers. An integer is just a rational number where the denominator, b, is 1. For example, 5 is the same as 5 over 1. All integers are rational numbers. The rational numbers have a number of friendly properties, like we can freely add, subtract, multiply, and divide rational numbers, and the result will always be a rational number. This makes the rational numbers what mathematicians call a field. Another way to conceptualize the rational numbers is as numbers with a finite or repeating decimal representation. Numbers like 4, 0.5, and 0.3 repeating all fit the bill. As robust as the rational numbers are as a number system, there are still some numbers that we haven't accounted for, no pun intended. What about pi? For those of you who don't know, pi is defined to be the ratio from the circumference to the diameter of a circle. Note that this value is the same no matter how big the circle is, because all circles have the same proportions. Since pi is defined to be a ratio, we might hope that it's a rational number, but it turns out that the circumference and diameter of a circle cannot both be integers at the same time. If a circle has an integer diameter, it doesn't have an integer circumference, and vice versa. While this may seem like an obscure little factoid, it actually has far-reaching implications. It means that if we want to do any arithmetic with the dimensions of circles, we need this number. Pi is an essential quantity in geometry and trigonometry, and from there it makes its way into all kinds of applied math fields. The bottom line is, we really like pi in our number system, but since it can't be represented as a ratio of integers, it's not a rational number. So it's time to learn about the irrational numbers. The same caveat I had about the term rational applies here. Irrational doesn't mean beyond reason, it literally just means cannot be expressed as a ratio of integers. A better name would be something like non-quotient numbers, but again, we are stuck with irrational. Now, I'm sure many of you have seen the decimal representation of pi. The key thing to note here is that it goes on forever and it has no repeating pattern. Any finite or repeating decimal representation belongs to a rational number. This makes pi and other irrational numbers hard to work with, but fortunately we can approximate pi with rational numbers. 3.14 is an okay approximation of pi. 3.141 would be even better. 3.1415 better than that. 3.14159 better still, and I can keep doing this. If I take only finitely many digits of the decimal representation of pi, I've got myself a perfectly reasonable rational number. And if I add one more digit each time, I get a sequence of rational numbers that gets closer and closer to pi. Mathematically, we say that pi is the limit of this sequence. This isn't specific to pi. I can do this with the decimal representation of any irrational number. The key takeaway is that every irrational number is the limit of a sequence of rational numbers. In pulling out sequences and limits, we have strayed into the realm of mathematical analysis, another not particularly elucidating name. But it's an umbrella term for the field of mathematics that deals with sequences, series, limits, convergence, things like this. If you're not super up on your analysis, don't worry. I don't want to get super bogged down in the details here. The big picture is that we start with the rational numbers, and mathematical analysis gives us a tool for adding irrational numbers. Specifically, we're adding all limits of sequences of rational numbers to our number system. This is a process called analytic completion. I could do an entire video on analytic completion alone, but I'm probably not going to. The important result here, though, is that we get a new number system called the real numbers. We've come a long way since the numbers 1 through 10, so let's recap quickly. We started with the natural numbers, the numbers 1 and up. Then we added 0 to get the whole numbers. Then we added negative numbers to get the integers. Then we added fractions to get the rational numbers, and finally we are adding irrational numbers to get the real numbers. You can think of the real numbers as all rational and irrational numbers together. I'm not particularly fond of the name real numbers either, because it perpetuates this idea that some numbers are real and some numbers are made up, which is not a distinction that's actually borne out by the mathematics at all, but we're stuck with this name too. My quibbles with number system names aside, let's get into the properties of the real numbers a little bit. In the real numbers, we can evaluate any addition, subtraction, multiplication, or division expression, which is no huge deal because we could do that in the rationals too. But we can also take limits of sequences. This means that the real numbers are what mathematicians call analytically complete. You can't have a sequence of real numbers that converges to a number that isn't a real number. That may seem like a pretty arcane property, but it actually is really important. What it means is that the real numbers are a continuum. You can represent them with a continuous number line, and every point on this line is a real number. Whether it's an integer, a fraction like 1/2, an irrational number like pi, all the real numbers fall along this line, and every point on this line is a real number. That the real numbers represent a continuum makes them ideal for representing continuous quantities like time or temperature. Now, reasonable question. Are we done? We've got a number system that can represent an entire number line, so that seems pretty good to me. But there are still a couple things we can't do. Remember this guy, square root of -1? You can't take the square root of -1 in the real numbers. There is no real number that, when multiplied by itself, gives you -1. Similarly, while we can solve all linear equations in the real numbers, we can't solve all quadratic equations. This equation, x squared plus 1 equals 0, has no real solution. There's no real number I can plug in for x that will make this equation true. So what do? Well, we do the same thing we've done every time. We add more numbers. This is where this guy comes in, I, the square root of -1. To justify the advent of the imaginary number I, we're going to reach into the toolbox of a mathematical subject called Galois theory and grab a tool called a field extension. Galois theory is a subfield of abstract algebra named after 19th century French mathematician Évariste Galois. What we're going to do today with field extensions bears actually very little resemblance to the work that Galois did during his lifetime, but whatever, it's still his theory. And if you're interested, there's actually an entire Wikipedia article titled Things Named After Évariste Galois, so that's a wild read. Anyway, moving on, here's how a field extension works. Step 1, pick a field and a polynomial equation that has no solutions in your field. In this context, field means a number system where you can add, subtract, multiply, and divide. Our field is the real numbers, and our polynomial equation is x squared plus 1 equals 0. Step 2, add a new number to your field and define it to be a solution to your equation. Our new number is called I, and we define it to solve this equation, so we know that I squared plus 1 must equal 0. And if you squint and tilt your head at that equation for a little bit, you'll see that that means that I must be the square root of -1. And then, things happen, and we get a new number system, the complex numbers. Jokes aside, I don't want to get into the nitty-gritty of how a field extension works, but what we're actually doing is adding the element I to the real numbers. That's what that RU squiggly bracket I means, the real numbers union the set containing I, and then we take the algebraic closure of that set, which basically means we take all sums and multiples of I with real numbers and add those to our set as well, so that the result is closed under addition and multiplication. If you followed that, great. If not, don't worry too much about it. The important takeaway is, if you've got a polynomial equation that you can't solve, there is a well-developed method from Galois theory for extending your number system to create a new number system where you can solve that equation. Doing this with the real numbers gets us the complex numbers, numbers of the form a plus bi, where a and b are real numbers and I is the square root of -1. The complex numbers retain all the nice properties of the real numbers, like we can evaluate any addition, subtraction, multiplication, or division expression, and we can take limits of sequences. In other words, the complex numbers are analytically complete. But the complex numbers have the additional property that we can take any square root and solve any polynomial equation. This means that the complex numbers are what mathematicians call algebraically complete. So we really got a lot of bang for our buck with that field extension. We added this element I so that we could solve one polynomial equation, and seemingly as a byproduct, we can now solve any polynomial equation and take any square root of any negative number. Handy, right? The skeptics among you might still reasonably ask, didn't we just make up I? Like, fancy terms like Galois theory and field extension aside, didn't we just make it up? The answer is yes. Yes, we did. But that's actually no different than what we've been doing this entire time. Recap number 2. We started with the natural numbers, counting numbers from 1 and up. Then we made up an imaginary number called 0 to make the whole numbers. But we didn't stop there. We let our imagination run wild. We made up more numbers. We made up negative numbers, we made up fractions, we made up irrational numbers, and finally, we made up the eponymously imaginary number I. The imaginary number I may stand out here because it's less familiar, but really it's basically the same principle as when we added negative numbers so that we could subtract 10 from 5. In the whole numbers, you can't subtract 10 from 5. It doesn't make sense to take away 10 of something when you only have 5. That expression can't be evaluated. But in the integers, it can. We have a theory for keeping track of negative quantities. The complex numbers are the same way. In the real numbers, there just isn't a number that squares to get -1. We don't have one. But in the complex numbers, we do. And lest we forget that this entire structure we've been building is actually just a castle in the sky, I would remind you that we made up these numbers too. It's not like we got the natural numbers on stone tablets from the math god or something. At least, I'm almost positive that didn't happen. From my perspective, all numbers are imaginary. Right? Numbers are an abstraction that we came up with because they're useful. They help us describe and understand the world around us. They allow us to solve problems, they help us store and analyze data, they help us model and better understand relationships. They're wonderful, useful, beautiful, imaginary things. And I don't think we should place all these requirements on what constitutes a real number beyond, hey, they make sense and they're useful in solving problems. With that, I think I've hit the main points I wanted to hit. Our notion of number has been expanding over time from highly intuitive numbers like 1, 2, 3, 4, 5 to complex numbers, which are really just the next logical step in expanding our system so that we can solve more equations. And yeah, a lot of our number systems are kind of badly named. Before I let you go, though, I'd like to pose one last question. The complex numbers are an algebraically and analytically complete field. We can solve any polynomial equation and take any square root. So now we're done? We've explored all the number systems there are to explore? The answer is, of course, no. There are plenty of other systems out there. Vector spaces, finite fields, matrix groups, to just name a few mathematical complexes that are expansions of or alternate versions of the number systems that we've studied today. The sky's really the limit on these. Let your imagination run wild. Anyway, that's a brief overview of numbers. Thanks for watching.